Okay, so last week we learned about some, I can do unit 3, right? I think this quantum statistics, Bose Einstein distribution law. So from there, I'll start. I have started. So last week we learned about some importances of this quantum statistics. Okay. So quantum statistics comes into picture where classical statistics or classical mechanics simply fails. Okay. So Maxwell Boltzmann statistics is a classical statistics, and whereas this Bose Einstein and Fermi Dirac statistics are quantum statistics. So we learned about when what type of particles obey Bose Einstein distribution law, or when particles are indistinguishable, so they have integer spin, okay, integral spin angular momentum, and then yeah, and photons, then H1 atoms and phonons, they obey this Bose-Einstein statistics. So Fermi-Dirac statistics, like particles are again indistinguishable and they have half integral spin. Then electrons and then protons, so they obey Fermi-Dirac statistics. And also the particles that obey Fermi-Dirac statistics are like they also obey Pauli's exclusion principle. Okay. I hope by now you have read about this Pauli's exclusion principle in quantum mechanics. Okay, so today we used to quickly check what distribution of particles in different types of statistics. Okay, suppose you have two particles, and how would you distribute those two particles in different types of statistics? Different types means in Maxwell, Boltzmann, Fermi Dirac, and Bose-Einstein. Okay. So the distribution of particles and hence the number of macrostates in the three types of statistics will be different on account of different basic assumptions. Okay. How can you distribute three particles in each of these three statistics? That will differ because of different assumptions of these three types of statistics. Okay, suppose let us first look at Maxwell-Boltzmann statistics. Okay, suppose we have two particles and three cells. Okay, you say this, we have two particles and three cells. Okay, the number of ways in which these two particles can be arranged in three cells depend on the type of statistics applicable to the particles. Okay, suppose okay, suppose let us consider Maxwell-Boltzmann statistics first. So in Maxwell-Boltzmann statistics, what was one of our assumptions? One of our assumptions was that the particles have to be distinguishable. So if the particles are distinguishable, okay. So in Maxwell-Boltzmann statistics, particles are distinguishable means we can separate one particle from the other. Suppose the particles are A and B, small a and small b. Okay, so then as per Maxwell-Boltzmann statistics, in how many ways can you arrange them in three cells? So we are considering about three cells, two particles and three cells. In how many ways we can arrange them in three cells as per Maxwell-Boltzmann statistics? Okay, so let us see. So here we have three cells, 1, 2, 3. Okay, so we have three cells, first cell, third cell, second cell. So how we can arrange these two particles A and B? Okay, A and B are distinguishable particles. That's why we consider that two particles, let them be A and B. So in the first cell, we can keep two particles because there is no limitation. In Maxwell-Boltzmann statistics, there is no limitation on the number of particles that can be accommodated in a given cell. Cell is just a compartment. Okay, cell is just a place where you can keep the particles or you can arrange the particles. Suppose in the first cell we put both the particles. So AB does not mean that they are multiplied. Here it is not multiplication. Here A and B together have been kept in the cell 1, whereas cell 2 and cell 3 are empty. Okay, so this is the first arrangement. In the second arrangement, the first cell is empty, and in the second cell you have put both the particles A and B. Okay, third cell is empty. In the third arrangement, the first and second cells are empty, and in the third cell you have put both the particles. Okay, and first and second cells are empty. So in the fourth arrangement, in cell 1 you have put the particle A, and in the cell 2 you have put the particle B, and the third cell will remain empty. Okay, because we have only two particles and three cells are available to us. In the in the fifth arrangement, we have put the particle B in the cell 1 and particle A in the cell 2, whereas the third cell is empty. Okay. In the next arrangement, we have particle A in the cell 1 and cell 2 is empty, and particle B is in the cell 3. In the next arrangement, particle B in cell 1, cell 2 is empty, and particle A in cell 3. In the last two arrangements, cell 1 is empty. In cell 2, we keep particle A, and in cell 3, we keep particle B. Then again, in the last arrangement, ninth arrangement, the cell 1 is empty, and in cell 2, we keep the particle B. Uh, Sorry, and in the cell 3, we keep the particle A. Okay. So that way, how many arrangements can we have when we have two distinguishable particles and three cells? And I mean, we have to place these two distinguishable particles in the three cells. There will be 9 possible ways. 1, 2, 3, 4, 5, 6, 7, 8, 9. There will be 9 possible ways in which these two particles can be accommodated in three cells. Oh, sorry. Yeah, two particles can be accommodated in three cells. So is it clear? So yeah, so here it has been mentioned that in how many ways they can be arranged in the cells, that will depend on the statistics we are considering. So in Maxwell-Boltzmann classical statistics, so particles are distinguishable. That means we can distinguish one particle from another. And according to that principle, so these two particles can be accommodated in different ways in the three different cells. Okay. Okay, so in the note, okay, let me read what is written. If the particles are indistinguishable means you cannot separate one particle from the other. Okay, this is the case of the quantum statistics. The other two statistics, which are also known as quantum statistics or Maxwell, Boltzmann, and Fermi-Dirac statistics. Okay. Suppose if the particles are indistinguishable, then what happens? So these particles are suppose AA. Two particles, suppose both are AA. So last time it was AB because they are distinguishable. In case of quantum statistics, particles have to be indistinguishable, and let the particles be AA. Okay, uh, because both particles are same, so you cannot distinguish the two particles. Okay, suppose for in your class, in your particular class, BSc 6th sem, so each student is distinguishable because one student does not look like the other. Okay, so I can distinguish all of you. So but if there are suppose like twin brothers or sisters in the class, so it is, you have seen that it is often very difficult to distinguish twin brothers and sisters. So you keep on forgetting what was the, if you are new to them, so you keep on forgetting like, okay, who is this brother, who is the other brother. But for your class, that is not the case because each student is different from the other. But of course, here we are talking about very small objects, so that's why we have to consider this quantum statistics where the one particle cannot be distinguished from the other particle. So now, as per Bose Einstein statistics, in how many ways you can arrange them? Okay, so that we will see. So there will be 6 different ways of arranging these two particles as per the Bose Einstein statistics. So the note that I provided to you, I forgot to attach one page. Okay, so that page is missing, but I think that I can separately attach, separately upload today. Just give me a minute. I will share this. I will share this. Just give me a minute. Okay, new share. Okay, I hope you can see my screen now. So as per Bose Einstein statistics, you have two particles, and in how many ways you can share them? Two particles, A. See, we have again three cells, cell 1, cell 2, cell 3. So in Bose Einstein statistics also, there is no restriction on how many particles can be arranged in a, how many particles can be kept in a given cell. So suppose, so as per that, suppose in cell 1, we have two particles, AA. Okay, so both particles are kept in cell 1. Cell 2 is empty, cell 3 is empty. Now, suppose the cell 1 is empty. In cell 2, you keep both the particles, and in the uh, cell 3 is empty. Okay. Now, the another arrangement can be the third arrangement. Cell 1 is empty, cell 2 is empty, and in cell 3, you have kept both the particles. Okay. Now, suppose you have to arrange the particles separately now. Okay, earlier you two particles were kept in the same cell. Suppose now uh, you arrange them separately. Suppose in cell 1 you keep one of the particles, and in cell 2 you keep uh, the other particle, and cell 3 is empty. Similarly, in cell 1 you keep this one particle, in the second cell is empty now, suppose, and the third, in the third cell you keep the other particle. In the last arrangement, sixth arrangement, suppose cell 1 is empty, but in cell 2 you keep this particle A, and in the cell 3 you keep the other particle. Okay, so more than this, is it possible to have another type of arrangement for these two particles apart from these six arrangements? So 1, 2, 3, 4, 5, 6. So apart from these six, is it possible to, can we have another type of arrangement in Bose Einstein statistics? No, we cannot have. We cannot have as long as we have two particles and three cells. Okay, because here particles indistinguishable, so we cannot have. Okay. Okay, so I hope you have understood the type of arrangement in this case. Okay, so if not more than, okay, so this is how those two indistinguishable particles can be arranged in three different cells as per the Bose-Einstein statistics. So in how many ways they can be arranged? They can be arranged in 6 ways, 6 different ways. Okay. Okay, so now the last one is Fermi-Dirac statistics. So in Fermi-Dirac statistics, how you can arrange two particles in 3 cells. This is going to be interesting. So in Fermi-Dirac statistics, what are the two main considerations? The two main considerations are that the particles have to be indistinguishable. Just like Bose-Einstein statistics, indistinguishable means in this case also the particles are the two particles. So again, we are considering two particles and how you can arrange them in 3 cells. Okay, the particles have to be indistinguishable, AA, suppose, just like previous case, and we have 3 cells. But in Fermi-Dirac statistics, there is also another thing which comes into picture, is that the particles have to obey Pauli's exclusion principle. Pauli's exclusion. So I hope you understand, you have learned about this Pauli's exclusion principle. So it in atomic physics or quantum mechanics. So Pauli's exclusion principle stands that no two particles can be arranged in the same cell. In quantum mechanics, no two particles can have the same values of quantum numbers. But in statistical mechanics, so that we can arrange a little bit. So no two particles can be arranged in the same cell. That means in cell 1 or be it cell 2 or cell 3, two particles together cannot be placed. Okay. In cell 1, only one particle can be placed A. In cell 2, only one particle can be placed A. And the cell 3 is empty. Similarly, in cell 1, suppose is empty now. Cell 2, you can put only one particle, and in cell 3, you put another particle. And in cell 3, you have one particle, cell 2, suppose is empty, and the cell in cell 3, you put the other particle. So here so here it is not possible. So like Bose Einstein statistics, AA in the same cell is not possible. Similarly, AA in the second cell or AA in the third cell are not possible because they obey Pauli exclusion principle, and as per that, only one particle in a given cell has to be accommodated. Okay, so as per Fermi Dirac statistics, in how many ways we can arrange two particles in three cells? In three ways. Okay, in three ways, 1, 2, 3. In three different ways we can arrange those two indistinguishable particles in three cells. Okay, so that is the thing. So if we have two particles and three cells, as per Maxwell Boltzmann statistics, there can be 9 different ways of arranging them. And as per Bose Einstein statistics, there can be 6 different ways of arranging two particles in three cells. But in Bose Einstein statistics and also in Fermi Dirac statistics, they have to be indistinguishable. Indistinguishable means you cannot separate one particle from the other. And in Fermi Dirac statistics, apart from that, the fact that those particles have to be indistinguishable, they also obey Fermi Dirac statistics. Okay. So, sorry, yeah, Fermi Dirac statistics, they have to obey Pauli's exclusion principle. So as per that, only one particle can be arranged in a given cell. Okay. So there can be only 3 different ways of arranging the particles. Okay. So I hope you have understood how particles can be arranged as per three statistical mechanics. Okay, so after that, I hope you have understood this, and the note I will upload separately to Google Classroom. And
Sir,
now,
one question.
yeah.
Sir, the Fermi Dirac statistics, they can be like electrons,
Yeah,
and if like electrons, they can be like two electrons in same state.
No, see, electrons obey Pauli exclusion principle. So same state means what? You see, so one electron is, so you know, spin quantum number. So
Yes, sir.
S equal to plus half and S equal to minus half.
Yes, sir.
So
That is
if,
what I'm saying.
yeah, if one electron is having spin up, then the other electron is having spin down. Okay, so spin up electrons are having generally spin quantum number. I hope you are already familiar with these concepts of quantum numbers.
Yes,
So
sir.
yeah, so one electron can have plus half spin and the other electron can have minus half spin. So by general sign convention, plus half means up spin and minus half stands for down spin. So no two electrons can have like up spins. No, it is not possible. Or they can have both down spin. their other quantum numbers may be equal. So n, then l, ml, those quantum numbers may be equal, but where they will face inequality, they will face inequality when it comes to spin quantum number. Okay, so these arrangements are not possible. Both up spin or both down spin, they are not possible. So why not possible? It is simply energetically or thermodynamically not possible. Okay. So in thermodynamics, suppose you already know that two particles, like whatever with not particle, let me call it a system. Two systems, a system can exist in stable state when its energy is minimum, potential energy is minimum. And this particular configuration gives minimum energy of interaction or potential energy. That's why this is energetically favorable, not both up spin or both down spin. Okay. So was that your question? So that's why when we have just seen how the particles are arranged in Fermi-Dirac statistics. Suppose particle means electrons or protons like that, and since from spin quantum number wise they cannot have same value. So in each cell represents like one energy distribution. Okay, so we are talking about the cell. So each cell represents like one energy value. Suppose the second cell represents another energy value. The third cell like so this way actually the arrangements are done. So that is
Okay,
the
sir.
case. Mm. Okay, so next what we would like to discuss is this Bose Einstein distribution law. Okay, because Maxwell Boltzmann distribution law that you will learn in classical statistics. So we will start with Bose Einstein distribution law, and then there will be another Fermi Dirac distribution law. So you see, finally, what we have to find in the Bose Einstein distribution law is this particular equation. Okay, so this particular equation is what we have to uh, find out. Okay, so this is Bose Einstein distribution law. Okay, so it's going to be very like mathematical, or not mathematical but statistical in nature. So you can see the derivation in for examination purpose. You can reduce the derivation. Suppose if I ask you like derive the Bose-Einstein distribution law. So this particular equation 7, which of course I will explain, this equation 7 is the Bose-Einstein distribution law. Okay, Bose-Einstein distribution law. So how this happens? So let us check. Okay, it's mainly very statistical in nature, and you will come across several new terms. Okay, mainly these terms called thermodynamic probability W, and yeah, and so on. How the particles are arranged in what number of ways. So this factorials, etc., etc. Okay, so let us start. I don't know, we cannot finish it today. Tomorrow, I will try to finish this Bose-Einstein distribution law. Okay, so consider a system consisting of n independent identical particles. Okay, so yeah, so these particles have a definite energies or momenta, as well as they occupy definite positions. So they can be represented by phase points in the phase space. Okay, so phase space you have already learned previously. So it's like momentum and position space. Okay, so when you have to we have to find the volume of a phase space, so we have to consider both position and momentum of the particles. In order to determine the energy or momentum distribution of these particles in the most probable or equilibrium state, okay, energy and momentum distribution. So this is the thing that we have to derive mathematically. In order to determine the energy or momentum distribution of these particles in the most probable or equilibrium state, we divide the available volume in the phase space into a large number of components, okay, or called quantum groups or energy levels. Okay, suppose K, okay, large number of compartments, components called K. Okay, so K represents energy levels. So in order to find the energy and momentum distribution, so we divide the available volume into large number of components or energy levels. So each compartment here represents a small interval of energy or momentum. Okay. So further, we divide each component into elementary cells of size h cube. So h cube represents some type of volume. Okay, the compartment of each, the volume of each compartment. Okay, so compartments will be will be divided into cells and having volume h cube. Okay, so h is Planck's constant. So if further suppose that the size of the compartment is very big as compared to the size of the cells, so that each component contains a large number of elementary cells. Okay, so now let us see what are the cells, how many, what are the particles, how their, what are their energies. So let there be N1, N2, N3 up to Ni and Ni and then up to Nk. These are the particles. Okay, suppose these are the various particles. Okay, various what type of particles we already considered? Identical particles. Okay, these are the various types of particles. Mean energy values. So what are the energy values? So U1 is the energy corresponding to N1, U2 corresponding to N2, and then Uy up to Uk are respectively their energy values. Okay. In compartments numbered as, so these are the energy values and these are the compartments. Okay, because we have already learned that these particles are arranged in various compartments and each compartment relates to some energy value. Okay, suppose this U1 energy corresponds to the compartment 1, U2 energy relates to compartment 2, Uy energy relates to compartment I, and Uk energy relates to compartment K. Okay, uh, containing G1, G2, G3 cells respectively. Okay, so with these energy compartments, they contain, these are the cells G1, G2, G3, and so on. Okay, so what are the things we have to consider? The particles N1, N2 up to Nk, energy associated with each particle. Then this energy are actually like compartments. Okay, each compartment is associated with some energy, and these compartments are uh, they have, okay, the cells which are represented by G1, G2, G3 up to Gk. Okay, so the next, see the number of particles in the system. Suppose n number of particles are in the system such that N1 plus N2. So N1 is the number of particles in a given compartment, N2 is the number of particles in another compartment up to Nk, so that when you add up all the particles, so suppose the total number of particles that we get is small n. Okay. Okay, then now let us consider the ith compartment. Okay, ith compartment means suppose a general compartment. Suppose this one. So ith compartment means suppose this one. Okay, ith compartment. So it has Ni indistinguishable particles distributed among its GI cells. Okay, in ith compartment there are GI cells and it has Ni number of indistinguishable particles. Indistinguishable particle means since we are considering Bose Einstein statistics, so indistinguishable particles. Okay, in GI cells. Let us calculate the number of ways in which, yeah, this is important. Let us calculate the number of ways in which these Ni identical particles can be distributed among GI cells. Okay, so Ni particles have to be distributed in Gi cells, in Gi number of cells. So in how many ways can you do that? So that is where this statistical mechanics things comes. Okay, just give me a minute. So what we have to find out, in how many ways this Ni number of identical particles, okay, in the ith compartment. In the ith compartment, there are Ni number of particles, suppose, and how they can be distributed in Gi number of cells. To do this, we first choose the cell with which to begin the sequence. Okay, the choice can be made in Gi number of ways. Oh, okay, since there are Gi number of cells. Okay, so there are Gi number of cells, and therefore, in how many ways they can be arranged? Suppose in the first case, in the first instance, suppose this Ni number of particles can be arranged in Gi number of ways because there are Gi number of cells. Okay, the first particle. Okay, the first particle. First choose. Okay, so the first particle. So better I mention it here. The first particle may be chosen in Gi number of ways because there are Gi number of cells. Okay, this Ni number of particles have to be arranged in Gi number of cells. The first particle of all this Ni, that will be arranged in Gi number of ways. Why? Because total number of cells in Ni compartment is suppose Gi. Okay. Uh, okay. So GSS. Once this has been done, the remaining G minus G1, sorry, GI minus 1, the remaining GI minus 1 cells and Ni particles, total Ni plus GI minus 1 elements can be arranged in order. So once you have like arranged the first particle, so the remaining particles, so how many, when the one particle is kept in the first cell, so how many cells will be remaining? One cell gone, so it will be Gi minus one number of cells. And the Ni number of particles can be arranged in, so Ni is the total number of particles initially considered. So Ni plus Gi minus 1 number of elements can be arranged. Okay, elements, why we are taking elements now? Because an Ni number of particles are there. That's why in the first particle is suppose arranged in Gi cell, and then in general, Ni number of particles, oh sorry, so where are we? Okay, so Ni number of particles in general can be arranged in this many number of elements. So Ni plus Gi minus 1. Okay. So in according to like this mathematical or statistical rule, so in how many ways they can be arranged? So they can be arranged in total something like this: Ni plus Gi minus 1, then this factorial symbol. So in this many number of ways, the remaining Ni, Ni number of particles can be arranged in remaining Gi minus 1 number of cells. Okay, so this is as per statistical or like mathematical rule. Okay, so then what is the total number of ways in which this distribution can be arranged? So the total number of ways in which the distribution can be arranged is, now you have to consider all Gi number of cells multiplied by this arrangement, Ni plus Gi minus 1 factorial. Okay. So the number of ways in which the particles can be arranged in Gi minus 1 cell. Okay. And then since there are Gi number of cells, so total number of ways can be something like this. Okay, so this is purely, don't ask me how this happens, because this is purely from statistical mechanical point of view. Okay, so now there are some assumptions. As the particles are indistinguishable, the rearrangement of particles among themselves will not give rise to new distribution. The number of such meaningless permutations is this ni factorial. Okay, hence the above result should be divided by this ni factorial. Okay, so the arrangement of the particles themselves will not give rise to new distribution. So now, as per some rule of this arrangement, so this particular expression we have to divide by this ni factorial, because the number of permutations which will be meaningless because they cannot give rise to new distribution. So that is something like this ni factorial. So this particular expression has to be divided by ni factorial. So which is reflected in this probability expression. But there is one more step. Secondly, the distribution which can be derived by mere permutation of GI cells among themselves. Okay, so it is some GI permutation. These permutations also do not produce defined states, and we have like meaningless number of permutations. So this expression again has to be divided by this GI factorial term. Okay, because there are GI number of cells, and they also do not give rise to new distribution. So this expression further you have to divide by GI factorial. So now finally this WI is being calculated. So does the number of different arrangement or meaningful microstates for the ith compartment, okay, this should be ith compartment. For the ith compartment having any distinguishable particle to be distributed among GI cells is given by, so number of arrangements or meaningful microstates. Okay, so the number of arrangements can be finally written as something like this. So Wi is equal to Gi Ni plus Gi minus 1 factorial divided by Ni factorial and Gi factorial. Okay. So I think up to this, here we stop today, because our time is almost going to be up. And someone please take the screenshot quickly, and then you post it to WhatsApp group. Okay. So rest of the things and the distribution law we will discuss tomorrow. We will do the derivation tomorrow. But this is very, very like statistical in nature or mathematical in nature. Okay. So someone please take the screenshot, and then we end for today. We'll restart from here tomorrow.